This is a 2160 lecture 16, unbiased system identification. In particular, we discuss FIR model identification using the Laguerre series expansion. So you have no idea about the Laguerre, that's a French mathematicians. The end result is really amazing. But to reach there, you have to go through several challenges. And then if you get it, surely, you have a big smile. Yeah. Even though you don't get it, we have many materials for you to review and catch up with it, and also ask me. I'm happy to provide any assistance in that. The last time I talked about the two major things involved in the system identification. One is that whether you can get the true values, the true parameter values as you collect more data. Are you guaranteed to get the right one, right? That's a consistent estimate or unbiased estimate. They are basically the same under ergodicity assumptions. And then second one is actually how quickly you can get it, how many data points you need, right? What is the actually quality of your estimation or prediction, right? Identified model would be. So that's actually key questions. And then we introduce the central limit theorem, and end up with the nice the Gaussian distributions, and then you can find with how many data points you can get what the sort of accuracy, right? So I look at the first question, consistent estimate, unbiased estimate. This is a little the tough one. However, there's actually a good method in handling this issue. So that's we go back to FIR. That's the simplest one. Finite the impulse response. Impulse response is usually infinite, but we truncate it in a certain point, then we can, perhaps deal with something, tractable dimensions. So yeah, in this case, an FIR model, we have a mainstream. This one is from input to output. This is the main transfer function we like to identify. And in the case of a FIR model representation, this one is represented as the moving average, or just basically impulse response type of representation. So ut minus 1, ut minus 2, t minus nb. That's actually kind of moving average, right, of the input, the time sequence. Now we allow the noise coming in, which is colored. VT is not actually ET. ET is white and totally unpredictable. But here at this time, we allowed something colored one, HQ, okay? So suppose the goal is to just identify for the past GQ and no need to identify the noise dynamics, that the VT presumably coming from the white noise through this, the dynamic noise transfer function, and then it's colored. But suppose we just focus on the identification of the GQ. FIR has a very unique, important properties. So given the data set, you compute the least square estimate, basically ignoring this VT. Still, you get the unbiased estimate. That's actually the key point. So, just a quick analysis is this. Let's say the model is correct. Okay, this model is correct. And let the theta naught be the true parameter values. The data are generated therefore by this formula. So the model structure with this FIR model structure with the true parameter value theta naught. Okay, and then some colored noise. Okay, so if you just formulate just naively, this square estimate, you get the basically this is the FIR result, right? Here, R is actually this is the FIR explicit solutions, and R is coming from the phi transpose. You remember this matrix, right? Okay. Now, so into this YT, let's plug in this expression because this is the true measured YT, and then that comes from the process of this model with the true parameter values, right? So substitute this one into this, so you get this expression. Now we can distribute this to two terms, and both are, basically this guy is a scalar quantity, so maybe phi t can be placed in here, So first expression is R inverse, this picks up a phi transpose, and then theta naught can be factored out. It turns out that this term is basically a matrix R, so these two cancel out, leaving just a theta naught. Theta naught is a true value. So a true value plus this term. This guy comes from the second term, this times this, so Vt and phi t, right? And then R inverse. Boom. So, if this estimate, and it turns out to be a little bit biased, then it comes from this term. So if colored noise and on phi t, which is basically the regressor, picking up these U's into this, if these two are correlated, then you get the basically biased estimate. So, if we use the ARX model, which is pretty good one, and other matter of fact, but remember that the ARX, this phi t regressor contains not only ut minus 1, ut minus 2, but also yt minus 1, yt minus 2, right? Remember that? Now, this is Vt is not actually ET. Vt is colored, so it reflects the previous values, and it's dragging many things. So there's a good chance that the Vt and the yt minus 1, the yt minus 2 may be correlated. So that's actually the reason, ARX, we did a very careful job in doing that, right? And then our max model, moving average is more actually, complicated. So we use the, predictor, right? So we use the predictor. That's actually the best estimate. And we carefully crafted the best estimate, and then compare that one against the real measurement. That's what we did last week. However, the situation is different. Even though this Vt is colored, it is not just instantaneous ET, but once it goes through HQ, it may include some fragment of ET minus 1, ET minus 2, right? Which may be correlated with YT. However, if this regressor part contains only input the U, that is basically FIR model coming from this, and it picks up only U's to create the, basically this, the linear regression. Linear regressions, parameters B's are factored out in this way, clearly separated. If this is the case, we can design the input sequence, as far as we can provide the input sequence which is not correlated with the VT, this term disappears. This term disappears. That said, we get the true theta naught. So our estimate is basically unbiased. This property is actually obtained because we do not include in the model regressor, autoregressive terms, Y's, but purely input side, moving average. Okay. So let's actually push this directions. If FIR is actually usable, no matter what sort of a noise comes in, we are guaranteed to get the unbiased estimate. Now, pros and cons, right? So pros, obviously, it is an unbiased or consistent estimate. However, FIR tends to have many parameters to identify. If you somewhat precisely model some systems with the FIR model, impulse response prolongs a long time, and oftentimes it extends to 50 to 100 parameters, 50 to 100 sequence. That's really hard, right? Of course, this is a case when you have a somewhat slowly decaying mode. Okay, some slow pole is involved, then this one is to happen. It doesn't go down very quickly. So you have to include the many terms, and then that turns out to be theta dimension is extremely high. So 100 parameters, how can we actually assure that all 100 parameters to be estimated correctly? Surely you have a difficulty to create the input, which is persistently exciting all 100 parameters. And then also you worry about the slow convergence. Each of these components may have a very small contribution or, a contribution in predicting the output. In other words, the sensitivity of the output, to these parameter values is very, parameters are very small. So it's very slow convergence. So that's a problem, okay? Now, so what should you do? Here's the actually a nice technique, nice solution. Now we use some technique, in particular Laguerre series expansion. So time series data compression. So the data compression, that the image data compression, that's a spatial data compression, it, right? JPEG, and the JPEG is not that very effective, but I know MP4 is a pretty good compression. Now music too, the time sequence data too can be compressed very effectively. And one of the techniques along that line can be used for our system identification program. So the original direct FIR, you have input and then one time step back, the two time steps. We create the UT minus 1, UT minus 2, blah, 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 and then take the weighted average. That's actually moving average. That's actually YT, right? So if we do so, this NB tends to be very high, sometimes 50, 100, and that's very difficult to handle. So instead of doing this, what we do is input the UT is go through some filter, which we'll introduce later, some filter, L1Q, and then create the some processed signal X1, X2, and then Xn, and hopefully this actually N is much smaller than the original NB by designing a particular set of filters here. So for this small set of filters, we actually going to just a standard least square estimate to predict the output Y. So it is somewhat maybe you recall principal component analysis and the way to reduce the dimensions. Yeah, this guy is actually on the similar directions, but then along the timeline. Okay, so with the use of some special set of filters like this, the original data can be compressed. Thereby, we don't need to estimate many parameters associated with it. Okay, so instead of using the original UT, we use XT. XT is to go through input is go through some filters, okay? And then it is very small. Okay, so now that's actually a quick summary. However, going through a real math, yeah, you need to review or study a few new things. And so let me just go through it quickly. So this particular page is actually involved in the lecture note number 10, section 10.2.2. So, transfer function using a time, shift operator, or, this is basically, transfer operator, GQ, this is the expression by using the impulse response, right? Not the finite, but infinite impulse response by using a Q minus K, right? So, yeah, no, we can actually write the output to, YT, by just writing this guy into this form, which is very convenient, right? So now let's take the Laplace transform of this, Laplace transform. Now what is involved here is basically K time step, time shift and operation here, right? So you recall that, if you do some, Laplace transform of time delay element, that is basically a time delay is, once it is Laplace transformed, it turns out to be exponential delta TS, right? Exponential delta TS. Delta T is sampling interval, actually, one time shift the delay, right? Well, in this case, moving forward, delays, you need a minus sign here, right? So, so once you take the Laplace transform of this, y is the Laplace transform equals, inside of this is basically a summation, right? Laplace transforms is linear, so we can just break down to the individual terms, and then hitting this Q minus K, that is basically transformed to, exponential minus delta T S and Kth, right? K's, right? Times input UT's, Laplace transform delta U. So now replacing, this in particular, terms, exponential delta TS by Z, we have so-called Z transform, right? Or the transfer function. So, replacing this by Z, it becomes a Z minus K. And then only the difference between this original transfer operator and this the Z transform and transfer function is Q is changed by Z. But I know it has a more profound, more important difference, because this guy is a complex function of Z equal exponential delta TS. Whereas this one is just an operator. This is transfer operator, okay? But this guy is a complex function. So we can actually use the many of the complex function theory and the properties, principles, in analyzing this. For example, we can define the poles and the zeros, right? So poles and zeros, you studied this, and since you're undergraduate, course, like, say, so transfer function in frequency domain, GS equals something, something, right? So your instructor said that, let's set the denominator to 0, then solve that one for S. That is actually, the poles, right? Set the numerator polynomials, set that one to 0, and then solve this one for S. And then you get the, 0, in this case, minus B2 over B1, right? However, let's actually somehow expand that definitions, because, transfer function may take many different forms. So back to this, 0 is defined to be a complex number, Zi, that makes transfer function Gz to be 0. So Zi, that makes this one to be 0. And then that's 0. And then poles are basically complex numbers that makes the transfer function Gz infinite. So if this kind of goes to infinite, that's basically, this one is, paused, right? This actually agreed with this definition, set this one to 0, that's actually something divided by 0. So therefore this G shoots up. So that's actually, how this one, the pose is defined. Okay, that definition is a little bit broader, so let's use that. Another, concept that we need to use is the following. So bounded input to the bounded output stability. This one is one of the most, sort of a primitive and widely used stability concept, in particular signal processing. So, you have a linear time invariant systems, and you consider the input sequence, and then the input is bounded, amplitude is bounded between, let's say, plus C and minus C. Then you look at the output. Output is also bounded. Output is always bounded as far as you provide the input that is bounded. That is bounded input, bounded output stability. Okay, so with that definition of stability, that really makes sense, right? As far as input is actually bounded, output is always bounded. No chance that the output, despite just the bounded input, no chance that the output shoot up. So that's actually a BIBO stability. Now here's important theorem. Let's think about the transfer function GQ is BIBO stable. If this part, that's actually this, impulse response quotient to GK, if you take the absolute value and then you sum it, this absolute sum is bounded. It's bounded. If you are familiar with the little bit more advanced math, this basically L1 and a major L1, and it does exist. If this is the case, the system is BIBO stable. So let's actually prove this, why this is the case. Okay, so look at the examining the output YTs, absolute value. So this is just a definitions, right? Now we take the absolute value for each term. So this one is generally bigger than this, right? And this absolute operation can be taken for each of them. So divided into this. And then here, the things. So this is the absolute value of input, right? And as far as we assume that the input is bounded, this can be bounded by C. So replacing this by C, it becomes even bigger. So, something times C, right? See this guy, and then if, this terms is basically, bounded. That's basically assumed here. This is assumption. If this one is bounded times a constant, it's also bounded. Right. So, we just showed that the output 2 is bounded. So that actually meets this definition. So, when you look at the transfer function, think about the absolute, summations of GK. And if that one is, finite, the system is, stable. Okay, let's use that. Now, BIBO stable systems, it has nice properties, and at this time we use a little bit on the complex of functions properties. Now, perhaps before going there, maybe I should point out that the relationship between discrete time versus continuous time frequency domain relationship. So that this is the S-plane, complex plane, and continuous time transferred to a frequency domain, the GS. That the stability of the systems is basically examined by looking at the order pose. If the order pose exists the left-hand side and no pose on the right-hand side, the system is basically stable, right? Now, and the actual discrete, the time systems converted to the Z transform. This imaginary axis and the S-plane is converted to the unit circle and the Z-plane. And then inside of this unit circles is basically mapped to the left-hand side of S-plane. And the right-hand side of S-plane mapped to the outside the unit circle. Okay, so perhaps many of you know it, but if not, then please actually keep this one in mind. Okay, now let's actually consider Z transform transfer function GZ. That's actually a Q is now replaced by Z, right? GK Z minus K. So then if you take the absolute value of this, this is bounded by this, right? Bounded by this, because take the absolute value for each term, so it can be written in this way, and the product can be taken individually to compute the absolute value, right? So looking at this, we can make the following interesting observation. If GQ, this system, is BIBO stable, okay, let's think about the value of Z. That's actually the inverse is to be less than or equal to 1. In other words, an absolute value of Z is actually 1 or greater than 1. That says that this is basically a unit circle, right? From here to this edge is actually length is 1, so delta Z equal 1 is basically mapped to a circle, unit circle, and a complex Z plane, right? So if absolute value of Z is bigger than 1, which means that the outside of this unit circle, then what? This guy is basically every term is basically not greater than 1. So replacing this by 1, or bounded by 1, you can actually get this expression where Z minus K is replaced by 1 and actually make that one even bigger, right? So, yeah, if BIBO stable, this L1, or I would say that absolute summation is basically bounded. So what this means is that there is no pole on and outside the unit circle. Remember the definition of a pole. If you put that particular value, say Zi into this shoots up, right? But this says that no, it doesn't shoot up. It doesn't diverge. That said, this transfer function does not have any poles outside of the unit circle. So outside the unit circles in S domains is basically right-hand side of the complex plane. So no poles on the right-hand side. What that means? It's basically a stable systems, right? Stable system, right? So in this case, if a pole exists, that must be within the unit circle, right? It does not actually prohibit having a pole inside of unit circles to satisfy these conditions. Okay, so now let's treat this GZ, GK, Z minus K, this is some kind of a, series expansion. And this can be treated, because this is the complex of functions, right? This can be treated as a Lorentz series expansion of a complex of function. Yeah, if that said, that the above result mean that the complex of function GZ is analytic on and outside the unit circles. So now I scare you with another mathematical terminology, Lorentz series expansions. And maybe you don't know the difference between the Taylor expansion and the Lorentz series expansion. They are very similar, but the Lorentz series expansion it's broader, and it can be applied to the systems having the terms with the negative order minus k. So we had to use the Laurent series expansion. But I know it's very go side by side with the Taylor expansion. So if this kind of series expansion exists, the such a function GZ is called analytic. If it's analytic, always this expansion exists. Okay. So is that okay? If you have any questions, you can just raise a hand or tell me, directly. Okay. Perhaps you are okay. So now, continuous time Laguerre series expansion. Okay, so we use these mathematical tools to construct a to develop a method that can actually reduce the dimensions of the FIR systems. So if a transfer function GS, we have to think about three conditions. Strictly proper, that's actually a zero exists at s equal infinite. So it's a little bit strange statement. So at this time s is basically, but by the way, I just started with the continuous time Laguerre series expansion, and then later we discuss discrete time expansion, and they are very similar, but continuous time it's a little easier to understand. So let's do this first. Okay. So we deal with the GS, just a standard transfer functions. Okay. Now this actually has a zero on the at the infinite. That means that they're looking at the this kind of polynomials numerator versus denominator. If the denominator's order is higher than the numerator, as s tends to infinity, this becomes zero, right? So what this says is basically, if you push the s to infinity, s equal infinite, that is a type of zero, because that is to make this one zero. Okay. And the second condition is this function is to be analytic in the right hand, right hand plane of the complex domain. Okay, and also continuous along this line. If these three conditions are met, then there exists a sequence GK bar such that the GS can be expanded to this weird function. But the quotient is a GK something bar, which is a little different from the original, FIR quotient. Comes with a bunch of first order systems, something s plus a, and then s minus a times s plus a, and then many powered k minus first powered, and then k equal 1 to infinite. Okay, so yeah, this is kind of transformation we can make. And then a bar is to be positive constant. It's called the Laguerre pole. Okay. Now a few more steps. Please bear with me. There are actually a few more steps to go through. So let's consider a complex number. Okay. This is the proof. Okay. So yeah, we consider the following actually transformation. This is called a type of a bilinear transformation from variable s to variable z. The complex number s to complex number z, then the transformation is defined by this. Okay. So this one is involved in the previous slide. Oops. Yeah, but anyway, let me see. Yeah, okay, yeah. So, let's see. This one is to transform, map a point in a complex plane in S to another complex plane Z. right? So let's first pick the point S on this imaginary axis, and then let's compute the absolute value of this, and then let's look at the this versus this. S plus 8, magnitude is basically S going the plus directions, a bar, and you arrive at this point, and then the absolute value of this point is basically this length, right? And the S minus A, you reach this point, and then absolute value is this length. And as far as you pick the S in the middle, this imaginary axis, the lengths are the same, so this ratio is 1. Having said that, this Z, Z's magnitude is 1. So every point comes out of this and mapped to the unit circle and this Z plane. Okay, now let's pick the point S away from this imaginary axis, and again S plus A and S minus A. You look at this length versus this length. At this time, this one is longer than this, so this actually Z absolute value is bigger than 1. That means that all the points on the right-hand side is mapped to outside of this unit circle. Okay, so this actually a bilinear transform and having that kind of properties. Okay, so with that, the inverse, let's consider the inverse transform of this. We look at this one, S to Z, right? Now we like to have Z to S. So multiply S minus A to both sides, clear the denominator, and then correct the terms with respect to S. You get the solution S equal Z plus 1 over Z minus 1 times A bar. Okay, now S equal this guy. So Z plus 1 minus Z minus 1 times A bar. It's basically S. So let's replace S by this actually function put in here. And this is now the function of Z, right? And then we write it the Z bar Z. Now let's take a quick exercise example. Obtain G bar Z for the following GS. Okay, 1 over S plus 1, S plus 2. Okay, and this particular part is simple, but it's very important. So, please take a pad and a pen and please compute this one. You have 30 seconds. Yeah, please do it. Yeah, 1 over, S plus 1, S is now replaced by this function. And then actually, simplify the expression so that it becomes a transfer function with respect to variable Z. Just do it. Yeah, just do it. Yeah. Yeah, this trick is very important. So it's a simple things, but I want everyone do this by hand. Just do it by hand. Yeah, to appreciate the difference between GS and the GZ. Okay, my 30 seconds is pretty short, but I know you know what you need to do, right? Here's the answer. Are you doing something like this? If you use something like this, that's all set. Yeah, and cleaning up this, and it takes a little time, but I know you get the functions in terms of Z, which looks very different, right? Very different from the original one. And so we named this one G bar Z. Okay, G bar Z. Okay, so yeah, now we go to the key part. Okay, so we like to prove the theorem 1. Yeah, from the assumption GS is analytic in the right-hand side, right? Therefore, G bar Z is analytic outside the unit circle. Because we did that transformation from S to Z, and then you did obtain G bar Z, right? Right. And then, S, right hand side of the S domain is mapped to outside of this actually a Z plane, unit circle, right? So, G bar Z must be analytic outside of this unit circle. Okay. If this G bar Z is analytic, then it must be expressed as a Laurent series expansion. So, such, coefficient GK series, GK must exist such that this one is expressed in this way, Okay. So if you can get this expression, basically, Z is now refreshed back to S minus A and S plus A. You get the, something, close to the final result, which we like to prove over here. Now, reaching there, a few more steps are needed. So first, from the assumption, GS is strictly proper, right? This is the actually first, assumption we made. So, let's use this guy for computing this. So it said that 0 exists at S equal infinite. So, putting an S to infinite, this must be 0. Now we are dealing with the G bar Z. So let's see, as S tends to an infinite, where Z is really going, okay? So, let's look at the limit of Z as S tends to infinite. And Z is now with respect to S, you can write it this way, and S tends to, infinity, this becomes just 1, okay? So what this said is that, GS has a 0 at the S equal infinite. That means that the G bar must have a 0 at the Z equal 1, right? So namely at the Z equal 1, G bar Z equals 0. This implies that Z minus 1 must be a factor involved in G bar Z. So G bar Z must be written in this way, right? So, this must have Z minus 1 as a factor. So factoring out this, the remaining part is just left in this way, G prime bar, some kind of function. But we can write this one in this way where Z minus 1 is factored out. Okay. Now, just making a little bit more transformation. When you factor out the Z, it becomes Z1 minus Z inverse, right? So now actually, this guy, it's a little different from the previous one, but this must be analytic too. So, we just expand this one in this way, okay? I use a little bit of different notation. GK is used here, but I know this coefficient series is a little bit different because we are now applying it to, the properties of analytic complex function to G prime. Slightly different, so we can write it this way. There's 1 over square root of the 2a is this particular part doesn't make any actually major difference. Just quotient that may influence this guy scale as a scale, but it's not. The point is that this Laurent expansion does exist. Now we are almost there. So let's compute this, okay? So first of all, this Z, let's put this one into this. So this part becomes Z1 minus K, right? Z1 minus K. Z1 minus K. Now Z is basically, this guy, S plus A over S minus A, right? Let's take the, let's put this one upside down. So I said that the minus K becomes a plus K. So put this one in here, replacing this Z by this, but we put it upside down. Plus K, minus K becomes plus K. And then also Z, I just want to put this one, combined here. So K minus 1. That's because we have this Z over here. Okay. So this is the term we obtained. Now, this particular part, the 1 minus Z, sitting here, divided by 2A prime. So, this needs a little bit more computation, but this can be reduced to this form, square root of 2A bar over S plus A bar. So this is exactly the same equations we wrote in the why this one doesn't go back? Oh, okay. Yeah, this is the theorem 1. We wanted to prove this. Okay, so what's the point? What's the point? And we had a lot of mass. Well, what's the catch? So here's the catch. Okay, remember our objective is to reduce the order of FIR model, right? Something slowly decaying, poles, prolongs the convergence, right, of FIR, response. But such a slow pole, such a pole is located near the origin or the imaginary axis. Remember that if you have a pole which is very close to the imaginary axis, this is actually decaying very slowly, right? And sometimes the pole which is closest to the imaginary axis is called the what? Dominant pole. Perhaps you remember that the 244 or 214s and that kind of stuff. Okay, so poles are slowest poles. So this one is really actually bottleneck, to reduce the order of FIR model. So shooting this guy. Okay, so in this case, let's actually set the Laguerre poles. Basically A must be positive. So we just look at the distance from this imaginary axis to this P1 in the negative directions. So this one is really a real pole over here. So put this one in this way. So if you do this, interestingly, yeah, this pole close to imaginary axis is a very bad guy. Transfer. Excuse me. Transferred to the origin of the Z-plane. So you remember that this imaginary axis is mapped to the unit circle, right? And actually, if the poles are sitting in the right-hand side, it's unstable, right? So this is the boundary, and so is this actually a unit circle. So outside of this, unstable. Inside is stable. As you are getting farther from this unit circles, it becomes faster and faster. Okay, away from this, actually decay more quickly. So this ball, the kind of slow guy close to this imaginary axis, is mapped to this point, which is farthest from this, boundary, unit circle. So this must be extremely fast. Basically, it converges instantaneously. The slow pole can be relocated by using the bilinear transformation. If we set the Laguerre pole at the slow poles, itself, then this guy, let's actually confirm where this one is going. We use this in a transformation, the transformation test, right? And then now we set the A to be minus P1. So putting this one here, S minus P1, S plus P1, right? And what we'd like to do is to this particular point to P1 is to be moved to a certain point. So S is now evaluated at S equal P1. So setting this S equal P1, this becomes 0. So Z is 0. So that's actually going to this point. And this means that a very quick convergence. With the slow poles being mapped to the origin in the Z-plane, the system's impulse response in the Z-plane converges almost instantaneously. Furthermore, we have another pole P2, but then this one is somewhat close to P1. They are also mapped to something close to the origin. So overall, the response is very quick. So you can truncate this impulse response with just a fewer parameters. Now, discussing this to this point, I'm afraid to say some of you don't recall what you learned in the undergraduate control subject, post-zero analysis. So do I need to review that a little bit? Yes, no? Or is someone nodding? So we'll do that. Okay, here are the things. So, this one is S-plane. Okay, this is just a standard the transfer function, the pole zero analysis, that's a story, right? Depending on the location of the poles, you can actually see the response it associated with some kind of a response, right? So if you have poles far from this imaginary axis, to say this point, and such pole, impulse response converges very quickly, just going down. Get very fast. But as this pole is getting closer to the imaginary axis, it becomes very slow, decaying, right? Slowly decaying. Now it's actually sitting in the middle, that's basically origin. This is marginally stable. So impulse response is just straight line. It does not move up nor moving down. If you see the poles on the right-hand side, it is to diverge. So if you hit this, the system that tends to diverge, unstable. Okay, now we discussed this in the Z-plane. So if the pole is basically away from this outside of that, away from this unit circle, it's unstable. So just moving up in this way. Right? If it is right on top of the unit circle, it is actually marginally stable because this line is basically, connected to this, mapped to imaginary axis itself. Okay, so inside of this it's stable, but close to this imaginary axis, just like this, it's very slow. It is close to this neutral, zone, the neutral, marginally stability. As you getting away from this unit circle, the faster. So this one is very close to unit circle, the origin. So it's very, very fast. So now do you feel comfortable with it? Okay, so what you can do is that, given some, possible pole locations of the systems, pick a Laguerre poles close to the dominant poles, such as this, the dominant poles. Then actually, map all these poles to the Z domain. And your goal is to place all these poles somewhat close to the origin, so that all the poles are confined within a small circle of radius R. As R getting smaller, and the system can converge more quickly. Okay, so that's the technique we'd like to use. Yeah, so we like to confine all the poles, close to the origin in the Z-plane. So if there are many poles are involved, we pick the Laguerre poles near the dominant poles. That is the pole closest to the imaginary axis in the S-plane, right? So G bar Z can be approximated to a low order and FIR if they are actually confined within the small, R from the origin. So this one is actually truncated with fewer terms. So N usually can go on to infinity and maybe pretty small. Okay, so let's work out a few examples. So, compress the, impulse response of the following transfer function using a Laguerre series expansion. So transfer function GS equal 1 over S plus 1 square. Okay, we have poles S equal minus 1, in the S domain, but a repeated poles. Okay, So, first, actually, inverse bilinear transform using this guy, we rewrite this GS, replacing S by this. You can write this guy. So in Z domain, pose, which makes this one infinite, is computed as Z1, 2, and we have two poles, but the repeated poles, setting this in denominator equals 0, solving for Z, you get this result, right? Okay, so depending on your pick of A, these are transferred to this domain, through this equations, right? So, our obvious choice is A equal 1. If set the A equal 1, these two poles actually both are mapped to the origin, right? So that must be very fast. That must be very fast. Setting the Laguerre pole at A equal 1, we can shift both poles to the origin, right? So let's see how fast they are to converge. So now we pick the A equal 1. So let's substitute A equal 1 into this equation GZ. That becomes actually something over 4 times Z square. So divided this one for each term, this can be expanded to 3 terms. The first one is a 1 over 4 constant. The second terms pick up this guy, minus 1 over 2 Z inverse, and then 1, 4 Z minus 2. Okay, this is the exact expression, but it's a finite. Okay, not the infinite, finite. As poles are actually placed at the origin, it's finite. Okay, convergent to second order. So what you need to do is basically you got the GS this expansion is finite, K equal 1 and 2, only 2 terms. So I just wrote the 2 terms. The first term is this guy, and the second term is this guy. And then you have only 2 parameters, G1 bar and the G2 bar, to identify. Okay, so what you need to do is basically incoming input signals is first actually going through these 2 filters, Q and L1Q, L2Q. Basically, filters comes from this one is L1, okay, and this other hole is L2. Okay, so input is coming on Y equal GS times US, right? So yeah, US is to go through this filter and this filter, right? And then we take the sum of these. That's actually output YT. So I know here we have a kind of unique filter. This impulse response looks like this, and then this one is something looks like this. If you go through this filter, it's actually only 2 parameters good enough, right? So in fact, if you go through least square estimate, you get the optimal result. G1 to G2 is given by this, and that is to give the exactly this guy. Okay.
So Professor Asada.
Yeah.
So in this case, like if you didn't know what the form of G of S was, would you treat the Laurent pole, or sorry, the Laguerre pole A bar and the order as hyperparameters and just see what works best for the system?
Hey, Charles, that's an excellent question. That's exactly the case. We don't know. But I know if we have some idea, then, you can try and assume the slowest pole maybe somewhere like this. Then you can make the case. Yeah. We can do some actually thought experiments. So let me show you the next example, which is to basically deal with such problem. So the next example is something like this. So at this time, 1 over s plus 1, 1 over and s plus 2. Okay, two poles, right? So, I just want to, show you that the exact value is not the necessary, but I know somewhat close to it, that makes a big difference. Okay, so let's actually assume this guy and then work out where to locate that a bar, right? So the poles of G bar, just going through the same process. S is replaced by that functions, and that GZ bar, the poles can be computed, and the two poles can be computed in this way. Okay, depending on the choice of A, the location of Z1, Z2 may be different, right? So I tried out 4 cases. Case 1, I pick A equal 1, so Z1 equals 0, and the Z2 is basically 1 over 3. And they are located, these 2 points, one is actually origin, which is good, very quick. But then the other one is sort of quick, but 1/3. Okay. If I pick the, case 2, just put the somewhere between these two poles. So, 1.5, A equal 1.5. Okay, well, original pose is -1 and -2, right? So somewhere just exactly middle is a -1.5. So taking the plus side, and I set the A equal 1.5, and then Z1 is -1/5, and then the Z2 1/7. So they are located here, -1/5, and then plus 1 over 7. Okay. Well, in fact, this one is basically closer than this guy. Okay, if I pick a 2 and one side is 0, but the other side is -1/3, that's basically a symmetric case, from the case 1, and then actually 2 poles in Z plane, here and here. If I pick the very pretty bad one away from it, 5, they are placing the 2 poles in here. So if you have some wrong estimate, pick the A equal 5 in this case, so that's not so much inefficient, right? Efficient. However, you have some idea, through poles or somewhere, in a group of poles or somewhere, you can pick something which is actually, satisfactory, bring all of them, in actually, decent, areas, like this. So that's actually a technique. So yeah, this is somewhat open question how you pick A, and it's actually depending on your prior knowledge. Yeah, prior knowledge about the field. Yeah, you can take. Okay, any other questions? Is that really clear? Because this one is based on many of the system dynamics control theories and the techniques and the principles. So it's not that easy, to get it. But I tell you what, this is something that only educated engineers can understand, they can use, right? So you are, one of those people who can understand that, right? So, you should be proud of it if you understand this, nicely. Okay, now I have to talk about discrete time, but this part is rather simple and then straightforward. So let's move on. So this is chapter 15.3, a discrete time Laguerre series expansion. In fact, in reality and in practice, we use this discrete time form much more than the continuous time form. So it's important to know this result. So the theory is slightly different from the continuous time. So we deal with the Z transform GZ from the beginning, and then this one must satisfy 3 conditions as before: strictly proper, and then analytic. And this is the main conditions: analytic, outside of the unit circles. Then it can be transformed to this Laguerre series expansion, where this yeah, this major part is slightly different from the previous one. 1 minus AZ over Z minus A. And this one comes from the bilinear transformation used for this expansion, and 1 over Z minus A. The others are just parameters. A must be picked from this range -1 to 1. Also, this constant k equal square root of 1 minus a squared times t is a time sampling intervals, or delta small t. That another notation we've been using. Okay, now key part is that at this time we use a slightly different type of a bilinear transformation. Now transformation from complex number z to complex number w. So this is another bilinear transformation. And if you take this bilinear transformation, it is to map z plane to w plane inside of the unit circles mapped to the same unit circle, and inside, outside. It preserves such stability and the phase and the conditions. Okay. Now, however, through this transformation, we can relocate the pose in here to somewhere, the different location here, right? And actually proof is basically the same thing. So I just, want to bother very much, since actually this one is analytic, W outside in the circle. And then it's proper, so we use the two conditions, and so from analytic, this can be written in this way. Lorentz expansion does exist, right? And then proper, so this term comes out. We can factor out this. The rest of the part is just to compute this, and the result is this. Okay, so this is the final result. Now, good thing is that at the end you have this result. Now, putting the z back to the time shift operator, z back to a time shift operator, z is now replaced by q, right? This time shift operator, right? So you can treat this guy output to yt equals gq ut. Now z is replaced by q, here. You get the kind of recursive filter, which I like to explain now. So ut is actually it's processed with these filters, right? So each filter can be written, say, LQQ and LKQ, and that applies to input ut. So let's see this. So this is same equation, right? So let me first look at the L1 k equal 1. So k equal 1, that this term actually goes away. So only this term, right? Only this term. So look at the L1. L1 picks the input, the ut, right? So after going through this first filter L1, it produces the signal. Let me denote it as x1. x1 equal L1q times ut. Okay, so x1 equal L1q ut, right? And L1, as I said, is coming from this first term alone, the k over q or minus a times ut. So this trick, the time shift operator is very convenient, right? You remember that one. So divided by q, it becomes denominator q inverse, and numerator is a q inverse, and the denominator 1 minus a q inverse, right? So from here, multiplying 1 minus a q inverse to both sides, first multiplied and applies to x1t is this x1t, and then this minus a q inverse, this guy applies to this one time shift to q minus 1. It results in x1t minus 1 with the coefficient a, right? Equals this q minus 1 ut becomes ut minus 1. So you can compute x1t by this expression. So you have, previous input ut minus 1 and the previous x1, t minus 1. You can update this with this expression. Now, interestingly, this x1 is basically ut times this, right? So now it's pushed k to 2, it becomes, this terms times this one, 2 minus 1 is 1. So just 1, this guy times this. Now ut is basically multiplied to this, but once ut is ut acts on here, that becomes x1. That x1 is operated further by this, filtered with this. So x2 should be expressed in this x1 multiplied to this operator. This comes from this guy, right? So, and again, divided by q inverse minus a, 1 minus a, q inverse, applied to x2 and x1. So multiplying this one to both sides, this becomes x2 minus a x2 t minus 1 comes here equal this side, this guy x1 t minus 1, and then minus a times x1. Okay, now moving this one to the right hand side, x2 t can be computed, based on the x2 at the one step back, and then actually result from x1, the current x1t, and a one time step back and x1t minus 1. Added in this way, you can actually compute the x2t. So in general, k step xk can be computed in this way. So this is a recursive formula. Isn't it neat? It's pretty neat and very quick. This one extremely fast. So not only in Laguerre series, but I know similar things are being used in the signal processing, quite effectively. Okay, so that's actually the most of the materials I like to talk about today. This lecture is connected to context-oriented problem number 3. So COP2 was a little actually, too much the hassles, and so I heard some complaints from some of you. Your comments are well taken. So COP3 is much lighter and enjoyable, I hope. So let me just introduce COP3 just briefly. So I think. Let me see. Let me confirm this guy. Okay. It's wrong. Excuse me. Oh yeah, this guy. Sorry. So this is actually context-oriented project number 3. I'm gonna release it soon, and the due date is November 6th, and you're gonna discuss it on November 6th, right? The due date is November 9th, excuse me. So, let's read it, okay? Figure 1 shows a cardiovascular network of a human. A high pressure, blood flow generated at the left ventricle is distributed through the arterial network. Okay, this is basically biomedical areas of the problem. One of the clinically important measures of cardiac function is cardiac output. That's how much blood is basically pumped up from the your heart. Well, and also we like to check the waveform, such as like this. This is your heart is producing this kind of pressure. But that's actually flow coming out of it. So however, to get the correct measurement, and in the ICU, people use the catheter inserted into the heart. But this guy, catheterization is very dangerous and a very costly procedure. It is desirable to estimate the cardiac output from your peripheral pressure using a hopefully non-invasive sensor, as shown in figure 2. So figure 2 is something like this. You put this, some kind of medical device and kind of waveform measurement device. It's not just blood pressure sensor, but it's a little bit more advanced one. But non-invasive. You put this one somewhere, different part of the body. Okay, but this. In order to get the original signals, the pressure and the flow coming out of your heart, we need to know this actually dynamics from your heart to your peripheral places, right? So this requires the identification of the arterial dynamics relating the peripheral sensor output YT to the input, the cardiac output UT. Okay, inverting this transfer function, you can probably get the original waveform. Okay, that's a problem. So it's really ambitious and interesting techniques. And yeah, one big challenge, however, is this. This is basically waveforms, coming from various part of the body. It includes carotid, brachial, and femoral here, and the radial, the many places. I just plotted all of them here. Depending on the locations, blood pressure, pressure waveforms are slightly different like this, but all of them converging to this slowly decaying mode, right? So in order to identify this systems, you have to deal with this slowly decaying mode. So that's why we like to use the Laguerre series expansion. So before going there, you need to study the richness of the signals by checking the rank conditions and so forth. So this is just a warming up problem. And then next, you use the Laguerre series expansion. The data is stored in the Canvas course locker, and if you download that one, it shows an interesting phenomena. Yeah, it does include some of the slow decaying one. So if you just use the naively just use the FIR model, you get the bad results. Yeah, it doesn't converge. You need 40, 50 terms in that. On the other hand, if you use a different, modeling, a different parametric representation, Armax model or ARX models, you have some significant, bias because of the colored, noise comes to this, place. Because even though the blood pressure is taken very, under complete rest conditions, but many things may interfere the signals, right? So the sensor is not that perfect, and so many of the color, the noise comes into your measurement here. So biased estimate is a bias involved in the estimate is a major hurdle that you have to go over. So in many ways, the FIR, as I emphasize, it's very good properties to cope with this kind of a problem. So and also another thing is that this is the real human, living humans, right? So many of this, system identity problem, you can design your input and shake it, with your favorite signals. But can we do that here? Your patient dies, right? So you have to use the natural input created by the patient heart, right? So in some way, the richness of the signals you receive are limited. So this is a place that you need something clever idea. And this FIR and combined with the Laguerre is a very good choice, okay? So I hope you get the good results with a reasonable, effort. So that's what you expect. Okay, any other questions? Anything? Yeah, but please. Yeah, go ahead.
One thing, sir. So you mentioned about being limited on what kind of inputs we can do for the human body. Is treating it as like the heartbeat as an impulse sort of is that close to reality? Because I was noticing like that slow decay seemed to go on for quite a few seconds. That would be longer, you know, considering like how many beats per minute you might expect from a person. Is there a lot of interference between like subsequent heartbeats in the signal you'd be measuring? I'm sort of out of curiosity.
Yeah. You know, of course. You know, so you know, it's a little different than the identification phase versus real measurement and estimation phase. Yeah, you know, identification phase. You know, we have to use something gold standard, correct input and then correct output, right? So for that purpose, we use some data coming from catheterizations, or we often use the pigs. Yeah, pigs are very close to humans, properties. Now, one more advanced techniques, which is really amazing technique, it's called the blind system identification. This is a technique that you don't need to access the original input, UT, like a heart beating. But if you place multiple sensors at your extreme, at your extremity or carotid or femoral, you need to use multiple sensors to detect that. If you use such multiple sensors placed at the different portions, under certain conditions, you can actually reconstruct the input without really knowing that. And without accessing that, you can identify the past dynamics. One from here to here, you measure this. One from here to here, you measure this. But these two, are not using this one. But if you can use these measured at the same time, you can apply the so-called blind system identifications, and this has been used not only for biomedicals but also wireless communications. If you have two stations receiving the same signals at the same time, if these two stations exchange information, they can actually characterize this channel dynamics. Yeah, the channel that's actually a little bit more advanced signal processing techniques. Yeah, so lots of things happens. Yeah. Okay, any other comments? So there are lots of math involved, right? So if you are a little bothered by that, yeah, I hope you can review some of the textbook which I recommended originally. And that's worth doing. Some basic properties and poles and zeros, right? And then the Z transformed, how it is actually transformed to Z domain. These are very useful, and not only for this subject and this area, but they're useful. So yeah, it's worth reviewing this if necessary. Okay. So that's all about it. Yeah. So have a good weekend, and very in any way extreme anxiety these times. But I hope you can survive. Keep smiling. Okay. Take care. Bye.
Thank you.
Bye-bye.